Okay. Hey everybody, welcome to week 2 of the OT Security Interest Group. Today we'll be covering the core OT components that are prevalent throughout OT security. He's currently still working on getting one of the demos we have set up today, but if you haven't already, join the Discord as well as sign in. So today we're going to kind of clear things up about the scope of the OT Security Interest Group, talk about how ICS architecture is built, dive into the actual components, talk about the security based around components in OT, have live demos like the one he's setting up, as well as have an interactive attacker tier list that we're going to do. So please feel free throughout this presentation to ask any questions. We're going to cover a lot of concepts. We don't expect you guys to take it to heart because we'll try to emphasize which components are really important to know and which ones are kind of good to know, but you don't need to know as much for this interest group. We just felt like we needed to cover each one of these. After last meeting, we thought we would more clearly define the scope for this interest group, which is all technology that can touch or impact the physical process is in scope for this interest group. This does include things like HVAC and fire safety systems. We'll go much more deep into HVAC and whatnot later on in the semester, but we will be covering a little bit of fire systems today. And we will be mainly covering components that are either connected to or are industrial control systems, which we kind of covered last meeting. So physical security like lock picking and badge reading is kind of out of scope for this interest group, mainly because there is a physical security interest group that focuses on that. While it is kind of in scope for OT, we're going to be focusing a lot more on the industrial control system side of the house. And all the stuff we're going to cover today, there is actually a lot more components out there, but the ones we're focusing today are much more prevalent in the OT security field.
Yeah, so one thing that we'd like to make exceptionally clear is the fact that this OT security and just OT in general, or let's just start using ICS because that's what we're going to be talking about today, is rapidly evolving, but the field is simultaneously rapidly changing in its leading edge and slowly changing in its falling edge, which is a fancy way of saying the new stuff is getting changed and iterated upon very, very quickly. And the stuff that's really old just kind of stays there. So you have this massive scope of, say, you have a sensor, and you might have a sensor from the same vendor that's the same model, but one was made 40 years ago, and then you have another one that's 20 years ago, and one that's current. And so the ways you might secure them is kind of different because there's this massive difference in the age of stuff.
And so the standard for industrial control systems architecture is the Purdue model, which also supports OT security when we're building out networks. So a lot of times, like we mentioned last meeting, you might have a flat network where everything talks to everything, which is bad for security. So some researchers came up with the Purdue model to help give OT security professionals a much better way of architecting out their networks. And it also separates everything into layers to maintain a hierarchical flow of data between the layers. But yeah.
Yeah, so here's another chart of it. Today we're going to be covering that OT section, level 0 through 2. And so we got the level 0 and 1, and these are going to be covering first. These are things that kind of are the physical devices that are kind of touching these industrial processes. Level 2 has some devices that are specific to hardware, but they're a lot more of this software level, and we'll get into kind of what that means when we get there. But first, we got to go over the scenario we're going to be using to ground all of our examples.
Yeah, so throughout this presentation, to kind of make it more digestible, we're going to be using a scenario as a reference point throughout, kind of have a lot more consistency throughout our examples and just kind of make it easier to understand. So we're going to, our scenario is going to be Star Wars themed, centered around Ewoks from the planet Andor, and the whole thing is around, after episode 6 of Star Wars, the Ewoks were fascinated by all of the massive complexes that they had on their planet, and they decided to build their own electric grid. This includes a control room, a main complex, and 2 remote substations. The diagram I'm about to show you, I just want to preface, it is representational. A lot of these OT environments, you'll have a lot of sensors, a lot of these different industrial control systems. So we're just going to be focusing on the bare process versus quantity, because we could really just make a massive diagram, but I don't think that's easy to understand.
Or beneficial. So yeah, here's sort of the basic outline of what we're going to be covering today. You can see, you'll understand a lot of stuff, but we're going to start with the lower level and kind of work our way up. So yeah, let's just get right into that. So the first level is this field level, or the physical level. So like, what is actually at this level? Well, we have things called actuators, which is just a generic term for saying something that like actually affects industrial process. It carries out a physical change. So these things can be things like pumps, transformers, or like a conveyor belt in your manufacturing facilities. Then there's things like sensors. I mean, like pretty self-explanatory with that name. They gather the real-time data. Without either of these things, you wouldn't be able to like know what's actually happening or affect any of the industrial processes. Both of these are really important to know. So some sensors, for example, is, temperature, a pressure sensor, a level, or like an optical sensor for light levels. Another one that's like not so important, we kind of mentioned it because it's really prevalent inside of like a power grid space, is an an intelligent electronic device, or an IED. Now, researching this was a bit annoying because it was, you'd search something up, okay, how do I do the IED? And you're like, it's like, so we shouldn't put a bomb in an industrial process. And we're like, okay, yeah. But essentially what there is, it's just think of it as like an airbag for a control module. We'll be going over that. He'll be going over that later towards the end when we're talking about safety control systems. So yeah, out of those actuators and sensors, we kind of have a couple categories with these field devices. So we have a simple category, and that sort of means that the actuator or the sensor is like a black box, meaning the only information we're getting from it is either, in the sensor case, just a single value. We don't know what's going on in the sensor. We're just getting a value from the sensor. Or with the actuator case, you're just sending the value to the actuator, and you have no idea if it's doing it, if it completed, or any data like that. The other category is smart. Simple and smart. Smart, it provides rich data about the process, can provide you multiple datas, almost multiple data points, kind of acting as multiple sensors, but it's one device. It also provides you diagnostics about the sensor itself. And you can also remotely configure them. So, that's great for security, but that's kind of the difference between the simple and the smart. Additionally, we have this thing called, with the input-outfield devices, sort of with an analog, which is like an electrical current and a wire, and a digital, which is like on and off, ones and zeros. That's not really important, but I just thought I'd mention that. So security-wise, when we're talking about these sensors and actuators, as far as the simple ones are concerned with the analog and digital, really, it kind of is limited to like if you have physical access for the most part. So if you physically tamper with the sensor, or do something with it. So say you got like a voltage regulator on your plant, and they like walk in there and just, I don't know, unplug it or something. Well, that's physical tampering. So that's not really cybersecurity, but that's something that can happen. More cybersecurity, you can spoof. So if you actually get access to like the connection wire that's sending the sensor information to the PLC, which we'll cover in a second, or the PLC to the actuator, you can send commands. And then you can also just jam the signal. That's going to be through like, cutting the cable, or if it's over some sort of like a Wi-Fi basically, you can also jam that signal. And if it's a smart device, then you kind of have these more sophisticated attacks, like you can actually do a configuration corruption or a denial of service. So some attacks that have actually like gone after sensors, mainly sensors, not really actuators, and we'll talk about why when we're talking about safety instrumented systems, but we have FuxNet, which is not Stuxnet. Don't know why they named it that, but that was a DOS attack, denial of service attack on sensors and sensor gateways. And then we have the Marucci Shire sewage spill, where the threat actor basically just sent commands to sewage pumps to just turn on when he wasn't the person, actually the device that was doing it. So that's spoofing. And then, Stuxnet, like they did everything. So in every single one of these categories, Stuxnet did something. So Stuxnet did a firmware attack on some of the actual motor controllers, so the actuators, to allow them to go faster than they were actually programmed to do at the start. And then we have this HART protocol rearranging attack, which was just basically they were able to do some smart config changes. And this is one of the only attacks that actually utilized the fact that some of the sensors you can actually configure. So yeah, smart change configs. Why do they matter? I mean, I kind of already said this, and it's kind of hard not to see, but it's, they physically sense and directly manipulate the industrial process. So without them, it's kind of like we wouldn't be here. Don't know why Chrome was fighting me there. But all right, now on to the control level. So what is at this level? There's a whole lot of stuff at this level. This is one of the most important levels when trying to understand what's actually happening inside of an industrial process and for the security aspect. So we got stuff called programmable logic controllers, or PLCs as we've been calling them. This basically controls the industrial process at a micro level. This is one of the most important pieces of hardware to understand in this talk. So if you come away with nothing but what a PLC is from this meeting, you'll come up a lot better. Then we also have programmable automation controllers, which we'll cover what those are, but they're basically they do advanced input-output systems for complex processes. Then we have remote terminal units, or RTUs. They basically are industry-specific logger to collect telemetry data. Then we also have the mastery terminal unit, or the MTU. Note, this is not the maximum transmission unit like in a packet. That also is annoying to research. But yeah, jumping right into what PLCs are, kind of like the most important part. They connect directly to sensors and actuators, and they also have two modes. So they have a run mode where they're running whatever program you have uploaded on them, and you can't upload something to them. Then they have a program mode where, depending on the vendor and the model, it can also be running, but in this state you can upload a program to it and change it. So this can be an issue with security, because if you want to make it so your PLC is more secure, you just switch it to run mode. But then the issue becomes a lot of these systems, you need to actually dynamically kind of update what you're putting in your PLC. So a lot of people will actually just leave it on program mode if it allows it to keep running. They're also designed for really harsh conditions inside of these industrial facilities. So sometimes when researching this, you might think, okay, well, why don't we just put an Arduino or a computer in there to do what the PLC is doing? And the answer is kind of the fact that, well, it's designed for these harsh conditions so it'll last a long time, and it's really fine-tuned to be kind of they're really expensive, but cheapest cost for having any waste. Also, they have a real-time operating system, which essentially just means that every single time it does something, it's sort of deterministic in the amount of time it's going to take. And it does this through a scan cycle, which we're going to cover right now. So a scan cycle has 4 parts. You have the input scan, where it's basically just going to read from that input module. Then it's going to write these to the input image table in the memory. Then the program's going to execute. Whatever you end up uploading to it, that's going to end up executing. It's going to grab all those points from the memory you just wrote in the input image table. And then whatever outputs you have set in your program, they're going to get written to the output image table. I mean, kind of sensing a pattern here. Then it's going to do an output scan, where it's going to read from the output image table and actually set the output modules. So as you can see, kind of a PLC almost is 3 separate parts. You have the input module, the central processing, and all the memory, and then the output module. And then does this 4th step, which is housekeeping, doing all the things that make the PLC still function, like updating counters, processing network information, stuff like that. So for a demonstration, we actually have a PLC here. Can you plug that in up there? Where we have coded, of course the wires are crossing, but coded a basic traffic light sense. So if you can imagine, we don't have an actual traffic light. So this is, say east-west going this way, and this side's this way. And this yellow guy, he just, for some reason, doesn't ever turn off. You can see it's red. They're both red. Same with this guy now, I suppose. Switching to green. And so you can see that, sure, we could have done this with a, Arduino, or, I mean, you could probably just do this with a breadboard. I don't know. This crazy stuff you can do with electrical engineering. But what this PLC is doing is we're not having it read any inputs for this program because it's just based on a timer. But, well, you probably can't see that. But there's little lights out here showing that it's setting an output. So it's running through this program and determining, hey, which light should I turn on? And the reason why it's a bit goofy down here is because I'm not an electrical engineer and I don't know how to wire stuff. And I wired this in 5 minutes just now. So one of them's plugged into the wrong thing. But all the outputs are getting set correctly. So it's slowly going through this scan cycle where it's reading the inputs. There are no inputs. Then it's running through its program logic where it's kind of deciding, hey, what state am I in? Am I saying everybody's green this way, but everybody's red here, or is it the yellow and red, or whatever that is? And you just kind of continue cycling through that. So yeah, that's that. If you have any questions or want to see the actual code for it, come up after the meeting and I can show it to you. It's on another computer, so it'd be really hard to get up there. But yeah, that's essentially, this is what a PLC can do. Oh, do I have the button work too? Hold on. Oh, it does. So what's supposed to be happening here is when I press this button, it's supposed to be like, so you know when it's late at night and like the traffic lights turn on to the blinking red for like a 4-way stop? So we also program that in. So it stops its normal process when it receives an input and just blinks of course only the left LED is working, but that's essentially what's happening there. Now, when talking about security with PLCs, I mean, it's a big one. You got firmware vulnerabilities. You also can have configuration and maintenance vulnerabilities. If in your program, you have the normal like bugs in any other program, somebody can exploit that if they know what inputs to send it. Additionally, you have the insecure protocols and network services that it uses. But then you also just have like, classic IT stuff, like you can just, denial of service it or get remote code execution on it or give it a rootkit, like everyone seems to do with PLCs. For example, Stuxnet, they gave it a PLC or a rootkit. Logic Locker was a ransomware worm on a PLC. Evil PC Attack, PLC Attack is a rootkit, but they actually did a rootkit to then pivot to actually infect the engineer's workstation if they come around and plug into the PLC to see what's going on with it. Their idea was to then get privileged access to that engineering workstation because that's going to kind of circulate through the network as well. And there's the Ghost in the PLC, which was a denial of service on the input-output ports. It was a bit crazy. If we can get into that at a different meeting if you want, but we're just kind of jumping through these. We also have Harvey, which is a man-in-the-middle rootkit. And then we got Iron Spider, which is a network rootkit. These are kind of how they got in. Then you also have PLC Blaster, which was some malware that they did a network scan on the PLC that actually crashed all the HMIs in a facility. And then Frosty Goop, which we're planning on having a meeting in 2 meetings from now. And so that's a really interesting attack. But as you can see, like there are so many attacks after PLCs. This is kind of like one of the most sought after things when you're looking at what attackers are going for. And next into the packs, these are essentially, it's just a PLC merged with the PC. It's sort of like more like processing power. Like the PLC, it'll only have like in the kilobits of memory, whereas the packs have a lot, as they say, which is like 1 or 2 megs. Then it's also built for complex domain processes, such as like a vision-guided motion. Say if you have some sort of like robot and you got cameras and you're trying to detect, oh, we need to move it here. That requires a lot of processing power and like real-time action. So that's what a pack would be used for. You also got like multi-axis coordinate motion. It's like CNC machines, if anybody knows what that is. And also you can program it in C, which is a high-level language when you're working with these things. And for the most part, I kind of agree with them now after having to program that guy for a bit. And yeah, they're very powerful compared to the PLC. But compared to a normal computer, they don't have very much processing power. But they're very fine-tuned for what their purpose is. Then we have the RTUs. RTUs are, they're a specialized data logger for a lot of these environments. They have really precise time stamping. And they're designed for low power. So the whole point of an RTU is, say in this power plant, if you have like a substation, you have your point where you're generating your power. Then you have the points where you're like managing where you're sending your power, so like the substations. And so you put an RTU at this, and basically what it does is it'll grab all the logs from inside your little substation area and send it over the internet or over the WAN network to your main control center. So when talking about like the attack and security involved with these, well, obviously you can have a denial of service, kind of like with everything in OT and ICS, because these are actually open to just the internet and not actually behind a lot of firewalls. You can also have a man-in-the-middle attack if you actually intercept a lot of these packets and kind of intercept them for sending information from the control room to the RTU, such as commands, and also the data from the substation back to the main control center. And you can also, do the classic stuff like remote code execution. Like one of the attacks on RTUs is pulled off by APT GhostSec. They attacked a bunch of Russian RTUs, and they ended up gaining root access through SSH, basically. And from there, they were able to DOS a lot of the Russian industrial systems because they were able to gain a foothold through these RTUs. So they're kind of important. Then we also have this thing called a master terminal unit. it's essentially just like a central server for a lot of these things to like collect all the data. Like the RTUs are collecting all the data, but they're not going to store them because they're meant to just kind of be like leave and forget. And they don't have much memory to store all this data, so they'll send it to the central server. It also is kind of for a little bit of the processing, but not a lot of the data processing. And also for sending controls back down from these higher systems like a SCADA, which we'll cover in a bit, and sending data up and down. So they communicate with basically everything. They communicate with PLCs, RTUs, the PACs, and the SCADA system. So they're essential to all of it. Sort of like why does the control level matter? And so they'd actually translate the digital commands into physical actions through the actuators. And so kind of like without these things, you wouldn't have a lot of the fine-tuning control that you need in a lot of these industrial processes. Like if you're dealing with a power plant and you have a large drain pull on one of your lines, you need to quickly shift where you're sending your power because you need to make sure you don't have a brownout or a blackout. So yeah, so far we've kind of covered this base level. We got the actuators and sensors covered, the things that control the processes, the PLCs, which are kind of in charge of making sure doing fine adjustments to those, the IEDs, which is kind of a safety instrument, and the RTUs, say in this remote substation A, to send all the data that's collecting there back to our main control center and also to send commands from the main control center back in. We haven't covered HMIs, we'll cover those in a second. Yeah. Any questions so far on the general picture of what we've built so far? Okay.
Okay, so now we're going on to the supervisory level. So this is referring back to the Purdue model is layer 2. At this level, you have the software and hardware that is supervising the components that we've talked about so far. So if we're going back to our EWOC scenario, this is what allows them to be able to see all their processes, configure alarms, and manage their grid centrally. So the human-machine interface, HMI. So this is kind of the central point of visibility for the operators to see the actual physical process. And this can either be in the factory floor or it can be in a control room. And so from a factory floor, it might just have one industrial process, whereas the HMIs in the control room will have multiple. So the core functions of an HMI, so as I've already talked about, it's a visualization. It displays the real-time process data on diagrams and graphics. It tracks equipment health and flags potential issues that may arise with the equipment connected to. It controls the actual physical process, so the operator can actually just go up to the HMI and click on things and actually make changes to the physical process, as well as alarms to notify the operators when things have gone wrong. So going back to our EWOC example, they might have an HMI that has all these circuit breakers on it, and the EWOC can kind of go up to it and click on what circuit breakers he wants to have open or on and whatnot. So going into the security side of the house, since this is kind of connected to everything in your industrial networks, if the attacker gets access to this, they can really manipulate the process, as well as a lot of the attacks we're going to kind of go into. A lot of the initial attack vectors are these vendor supply passwords that attackers are able to get to because they'll literally just put like admin as their password, as well as insecure remote access, which is basically weak network segmentation. They also, which we'll go into next meeting, is they use a lot of protocols that are literally just in plain text because they're all about efficiency, and so it makes man-in-the-middle type of attacks really easy to do. And so going into the actual attacks that have happened with HMIs, we kind of covered this last meeting, but the Ukraine power grid attack, Phantom Mouse, the attackers were able to click around, turn off all the circuit breakers, take out the power for over 200,000 people in Ukraine. And then there's a more niche attack, which is the Iran steel mill attack, which the Israeli-backed attackers or hacktivists were able to gain access to an HMI, which was accessible via the internet, and they were they were able to click around and make it so that the molten steel that was in the facility was spilling uncontrollably across the plant. And the photo in the bottom right, that's actually from like this webcam that the attackers put online, where the red circle is actually where like it would show like the workers running away because like the molten steel is like spilling everywhere. But pretty crazy attack. So Stuxnet, I know we've already kind of covered this quite a bit, but the thing that happened with Stuxnet with HMIs was that they replayed old sensor data on the HMI so that the operators are looking at their HMI and it looks all good, but we all know that behind the scenes a lot of bad things were happening. So it can also allow you to have a lot more obfuscation and whatnot. So from now on, we'll talk more about the software and hardware that supervises an entire plant or multiple. HMIs, they kind of are just with one kind of industrial process. But the things we're going to talk about are much, big, entire plants. So SCADA systems, this stands for Supervisory Control and Data Acquisition Systems. So they are data gathering oriented. So this basically means that they will gather data from all these different facilities that they're connected to that are in scope, and they allow a high-level overview for these operators to see their entire company. So like let's say the EWOCs, they can have their SCADA system where they can see everything from their main complex and both the remote substations all from one place. And so how does the SCADA actually work? Well,
Slide 43. What the hell? 44? Go back one. Okay, well, it's working now.
anyways, so going into how a SCADA actually works, well, it collects data from RTUs and PLCs remotely. It has the MTU server, which we already mentioned, which aggregates all the data. And then you have the historian DB that stores all that data. And then it also has dashboards. In most cases, you'll have an HMI that's also connected to the SCADA, so we'll visualize that process data. And wide area communications, it connects to these remote sites via a lot of different protocols, including Ethernet, fiber, cellular, or radio, and supervisor control at scale. So what I really mean by that is the operators are able to give like a high-level command, like let's open breaker 12, and the PLC will actually execute that logic and make sure that the high-level command is then executed safely at the lower level. So it just gives off a high-level command, doesn't have to deal with the actual logic and whatnot that a PLC deals with. So looking into security, there are very few attacks that actually target SCADA itself because it's really interconnected to everything. It takes in all this data. So there are vulnerabilities with the SCADA software itself, but it's not a main attack vector for these major campaigns. And sophisticated OT attacks, kind of like the HMIs, they try to trick the operators by making everything look good, but it's really not. And so from looking at the actual diagram, you can see that the control room, that entire thing is pretty much all connected to the SCADA. So a DCS, similar to a SCADA, but the scope is different. It focuses on a single plant and a single vendor ecosystem. So if you're a company that has building out an industrial complex, you may want to have all of your things easily integrated together. An easy way to do that is if you just buy everything from the same vendor, get all of your HMIs, your controllers, actuator sensors, all of that from the same vendor, as well as like the engineering workstation software, all of that from the same place. And it allows these companies to just have everything closely integrated, because that's a big issue in these industrial complexes. You have all these different vendors, you have to have then protocols that you have to use if you have using different vendors. So it just makes everything much easier when you have it all closely linked together. Where it's different from a SCADA is I kind of mentioned how you could have it have multiple plants, it's only one plant. So same kind of thing as the SCADA security-wise, but the big difference is because you have one single vendor, if that one single vendor gets compromised, then your full environment's kind of cooked. So going into the actual safety systems, so there's this thing called the safety instrumented system. So it kind of gives you that independent safety layer. So let's say your process goes haywire and you have physical damage that's about to happen if everything just goes crazy. Your SIS is kind of that safety net that tries to control the problem. So you can kind of see from that photo to the right how blue is like the process design. So like that makes it pretty easy to know like when to put like implement safety and all that kind of stuff, process control, and then you have your operator intervention, and then safety instrumented systems is your light orange layer, so right before you really have to bring in a lot more mitigation. It's that last layer of prevention before you have physical damage. So it has its own separate sensors, its own actuators, also has its own like safety PLCs. It's literally just an independent safety specific system. And it, of course, it only goes after when unsafe conditions occur. That's really the only time it does things. Its sensors and everything do send all of its data. It is always running, but it actually isn't doing anything physical unless an actual event were to occur. Yeah. So going into the actual security, if compromised, it could disable automatic safety shutdowns and really cause actual operators to possibly lose their lives, which is not great. Weak segmentation. One of the things is that with SISs, where we've seen from attacks, is the SIS is sometimes on the same network as things like the SCADA. So if someone gets into the same network, they pretty much have control over everything. They also have control over the safety of things, so they can pretty much optimize the physical impact on people. And the train attack is a big example of this. This was targeting the safety PLCs of the SISs, and the attackers uploaded a custom payload to the actual controllers to cause physical damage. These attackers were trying to harm people, not just the hardware and the complex. So that's kind of why we wanted to talk about SISs. It's not really a part of the Purdue model per se. It's not in any of the diagrams I've seen for the Purdue model, but we felt like we needed to kind of mention SISs because of that physical harm. So how this modifies our EWOC diagram, you can kind of see how the SIS PLC, or like the safety PLC, is connected to the actuators and sensors. It also sends data to the DCSs. It will also send data directly to SCADA if it's a different architecture or whatnot.
So we know this was a massive fact dump, but we thought we might as well just get it all over with in one meeting, and then we can be like, okay, now you sort of know all the stuff inside of these industrial processes. Now we can actually talk about the security and some of the things like that. So any questions about what we covered today?
When would you use a PAC versus a PLC?
Yeah. Okay. So what would you use a PLC versus a PAC? So essentially, and part of the issue with this is some of these like categories of like the devices started in 1980s or 90s. So in the 1980s or 90s, the PLC did very little. So the modern day, a lot of these fields are kind of getting blended, like a PAC and a PLC. They kind of do the same stuff, but generally speaking, you'd use a PAC when you're dealing with like visual data. So you need to process like an entire image and then make decisions on that very, very quickly for controlling like a robotic arm or something. So that's a case where you'd use a PAC over a PLC because you have a lot more data and throughput that you need to process, whereas a PLC is, you kind of just send it like, you got input on line 1 and line 3, what you gonna do? So stuff like that versus the PAC being like, okay, I see that there's a person walking here, so I'm gonna not move the arm there, but I gotta keep the motor here so it doesn't move. So stuff like that, a lot more complicated processes.
Would the IED kind of just be set, but kind of be like under the category of like SISs?
Yeah. It's essentially under the SIS category. Sometimes they can kind of be. The reason why I put it under field devices is because depending on, and this is kind of how it's always going to be in IT and OT, but depending on the place you go to, the IEDs might be under the SIS or they might be kind of with the normal functioning of things, but their general purpose is safety, whether that be for the people, but also for the actual devices themselves. Because IEDs are also put in charge of the controlling the power to the devices, such as the PLCs, not just to, in the power plant example, the outgoing power.
Do most attacks focus on one component, or they try to spread out and infect more things?
I mean, it depends on how sophisticated it is. Like for Stuxnet, they pretty much targeted everything. But I mean, most of the biggest attacks are from these nation states. So they generally do go after one or two. Like the Frosty Group attack that we're going to go into just targeted the PLCs. So a lot of it, I think it varies, I would say.
I think it has to do a lot with, say, it's just whatever their goal is, right?
Yeah.
And so if you have really bad security and your goal is just to interrupt this one process, then you're probably going to attack something that's lower down, like the sensors or the actuators or maybe the PLC. But if you're doing a more sophisticated attack, you have a broader goal to maybe bring down the whole plant instead of just a part of it. And they have good security, you'll end up needing to pivot through more devices in order to actually reach your end goal. Okay, if you haven't done so already, the sign-in and the Discord. Oh, the next meeting we plan on covering some of the more of this actually security landscape, some the best practices. We've kind of been mentioning them like network segmentation, but actually covering that along with some of the protocols that are being used in these networks, because some of them are actually pretty interesting, and some of them are interesting in a sense of, wow, that is surprisingly the more unsecure than I thought you could make it. So yeah, we're going to go over those, some priorities, some frameworks, best practices. So that's all we have for today. If you have any questions or want to talk about the PLC or something, come up, but that's all we have for now.
Yeah.
Thank you.